sessions, and I want to make sure you get that information if you're planning on attending. So I hope that you got that information. I hope it gave you a bigger picture of where we've been, what we're doing today, and where we're going throughout the course of the year. Today we're focusing on 2 algebra concepts and 1 strand 5 concept, and I'm going to shut up and let Steve do the rest of the talking because no one does it like Steve.
So notice, thank you, Emily, we finally got things working out where you all get the handout right at the beginning with all the things, so you can write notes, you can ignore it, you know that you've got it.
You got a good easel.
And a reasonably good easel, yeah, I mean it didn't fall when I actually, so, I mean, let's share. Very simple. My life has been as insane as ever. The good news is that at midnight yesterday morning, Thursday morning, I sent a 45,000-word manuscript that I've been working on for 6 weeks off to Heinemann. The second edition of the book I wrote 10 years ago is no longer on my lap. My family sold a building that my father bought 30 years ago in Manhattan. It's the last piece of assets that my parents have. My mother has gone through about $1.5 million in the last 10 years since her stroke. My brothers and I have been basically paying for her to survive for the last 8 months, and we are all being repaid tomorrow because the building sold and $1,000, a lot of money, was put into the thing. Would you just move the mouse, please? Thank you. I'm working on this World Bank project, and a week ago it was like, oh God, we're going to get fired, it isn't working, you guys are terrible, and we had a big meeting on Wednesday, and we met with the client yesterday, and I worked for hours on the plane yesterday. The good news is that the World Bank project is back on track, and we love it. My 32-year-old got a job, and at 32 actually has benefits beginning on October 18th, and for those of you who are my age, you know, that's unbelievable. That saves me $200 a month. One of my brothers lives in Washington, the other 2 are arriving, and all 4 of my brothers, my 3 brothers and I are having dinner tomorrow night at one of the nicest restaurants in Washington to celebrate the fact that Mom can now live to 120, that we get our money back and all that kind of stuff. You know why I do all this? Because honestly, an hour ago, when I met with the Estrella teachers, the high point of the week was none of those things. But it's when Charlie said, well, I have found that doing the bell work and I tried the formative assessment and it really seems to be working is the only thing that really makes me feel like a useful professional. And so I thank you, Charlie, but I thank each and every one of you because it means that unlike most professional development where it's in one ear, one out the other, who cares and all that kind of stuff, I have actually gotten to see today people beginning to do those things, people worrying about those things. And so I want to thank you for making those efforts and tell you that in the midst of all this craziness, your turn. So the kids have been here for 5 weeks. I don't want to hear the oh, woe is us and all the problems. I know they exist. Ready? Tell yourself the single neatest thing that's happened in a class that you're teaching this year that you feel others ought to know about. You have 30 seconds to think. The single neatest thing that's happened in your math class. 5 weeks under your belt. You have 15 seconds. Okay, I don't need to call on you. Yell it out. Tell the class. What aha moment? They can't hear you.
Sorry about that. The aha moment with a student who, up to this point, had not performed.
Ergo, we know that there's so much fog, there's so much uphill battle, and every once in a while the kids surprise us. Every once in a while the lights go off and we realize that we have had something to do with those aha moments when you know that they get it for the rest of their lives, as opposed to only being able to regurgitate it for another 2 minutes. Who else? Sir.
Yeah, I had a kid at the beginning of the block. It was like day 4. I noticed he wasn't taking notes. He was sitting in the back of the class. He was giving me the real attitude, and I basically gave him the real sobering, dude, you can't sit in my class and do this. Sent him up to Mr. Madden. And Madden had a long talk with him. And somehow, I don't know what happened, in the next 2 weeks, he started taking notes and he started doing the work. And this kid, yesterday, was actually doing some higher level stuff in my class. And I don't know if it was just that finally somebody showed that they're willing to work with this kid and not let him just slide through. I don't know what happened, but this was just one of those.
So what is the math and magic is what we all want to know.
Exactly.
I don't know if that was it, or if
Yeah.
he just realized that, wow, I'm not going to be able to sit in the back of that class and do nothing. I'm going to be
Maybe
required
the
to
amazing
do
case
something.
where the kid finally got the message somebody really cares. Who knows? Cool. That is exciting. Notice how it always comes back down to one kid. We think about all these classes and all that stuff, but it's the individual kid. Who else? Go ahead.
I have a fairly low-level sped student who I've had in the past and have really had to modify material for, and I have him in my pre-algebra class now, and it was so awesome. I worked with him on multiplying a 3-digit number by a 2-digit number, and he had never done anything past 1 digit by 1 digit before, and he was getting it, and it was just awesome. He was so excited, and it was just cool to hear him say, I've never known this before, and in 30 minutes he had it. And it was just kind of, I mean, you know, it wasn't, you know, quadratic, it wasn't anything, but it was so special to see.
But it reminds you that if it could happen in that situation, that it could happen in any situation. No question. There were 3 other hands. Right, Jessica, you had your hand up. You know Jessica, Jessica's new, she's at South Point. I understand that I watched Jessica teach this morning, but Jessica is here via the Peace Corps. She was in Ghana, right? Guinea, in West Africa. Jessica, your addition to this?
Oh, I had a student the first week that was sitting in the back, and she was like, I hate math because I suck at it. And so I made her sit in the front, and then I asked her to come to tutoring. And she came to tutoring once, and then she started tutoring every day. And she went from an F to a B+, and her last test she got a 98%, which is better than some of the super smart kids. And so it just shows that that I taught her something, and she's not bad at math like she thought she was.
Sure. And we all know that part of that's chemistry, part of it is just the right timing and all those things, and who knows, but it's so exciting when that happens. Sir?
Oh, I just had a gal in class, and she also didn't feel very good in math, and we worked with her a little bit. And as she went out the other day, I said, you know, Jeanette, I have a lot of high expectations of you. She says, you do? Really? And I said, yeah, I really do. And she brought a thank you card back the next day.
Wow.
So that was kind of cool.
Cool. That is neat. I saw 2 other hands. Go ahead, ma'am.
Well, ours has been more, not with one individual student, but as a department, we took on your advice of the first time you were with us,
Yep.
where you said, teach less, learn more,
Mhm.
and we've taken that on as our motto for the year. And so I've spent 3 weeks on teaching them how to graph lines. And instead of just, we totally, as a department, we got together and we redid our pacing of what can we take out of the curriculum, instead of trying to cover every single little thing, what's the most important, and let's make sure they really master those skills. We still want to hit some other things, but instead of just one section a day and keeping with that pace. And so, you know, what I find, yeah, there's still some kids in that class that can't graph a line, but for the majority of them, they can. And I've spent 3 weeks on it, but at least they can graph a line.
Nancy, so you know now that you have, your first name is?
Angie.
You and Angie need to talk because it's exactly what you talked about. And your sense of inadequacy over it, and we sat there saying, wait a second, what you did was right and all. So there's an example where you probably want to talk about what's going on. Hey gang, every book on PLCs says that one of the purposes is we celebrate the things that we do. We don't need to tell each other how hard it is being a teacher. We don't need to remind ourselves about just how uphill it is and all those things. I think that you just heard little glimpses that could have come from almost everyone's mouth. And if in fact you're sitting here saying, well, darn, there's not a damn thing I could have said, well, that tells you something pretty powerful. So I'll leave it at that. So, you know, Emily's been pretty clear. Emily said, go and deal with the problematic objectives. Go and deal with the ones where our test scores show that the kids in our high schools don't do well enough. And so, you know, I've taken some liberty with these things. So today we've got to deal with functions and quadratics, okay? Let's do this right, okay? In other words, more focused, there it is, more, what the hell is this? There it is. So today's focus is on functions and quadratics in problem-solving situations, where again, I'm going to do problems in problem context, as an opportunity to do what I think is most important other than just the math, and that is these first 4 Common Core State standards, okay? So that in fact, the mindset I have is, how do I give kids a reason to care? Right? How do I deal with reasons why anybody would want to learn quadratics? And how do I do it in a way that I've got kids making sense of problems, I've got kids reasoning abstractly and quantitatively, I've got kids constructing arguments, talking, looking at their work, and I've got kids modeling with mathematics. Because as you well know, whether it's Algebra 1A or it's calculus, that's really what kids need to walk out of. And so that's the subtext around these critical notions, importances of function. So, you all know that quadratics are a nightmare when they are taught in Algebra 1. They are a nightmare because we have to race through Algebra 1 to be able to do the stupid factoring, which is what it is, and get to the quadratic formula that nobody ever knows or remembers in any way, shape, or form, in a world where every normal human being who ever had to do that stuff either has a symbol manipulator and writes solve, or grabs the damn thing out and goes tracing in or zooming in on the thing, or does a table. And so you know that in some ways in quadratics we've been set up. And yet there's so much quadratics that's out there. So if you're ready, let's play. On your mark. Get set. Tell the person sitting next to you what you see. 3 different things that you see.
Yeah, I see a wall, I see blocks, and I see
All right, so here we go. Okay, I have Vanna White helping me today, right? Your first name is really?
Amanda.
Is what?
Amanda.
Is Amanda, okay? What should Amanda write? You saw?
Blocks.
Blocks, exactly right. There are blocks, wonderful. I've got the weakest kid in my class participating because they're blocks, of course they're blocks. And then I got the brightest kid in my class sitting on, she's 66 blocks. And she sits there and goes, how the hell do you know it's 66? 66 blocks. I hope it's wrong, right? It's not, I know. 66 blocks, what'd you say?
Pyramid.
You saw a pyramid, how nice. Wait a second, so, go back. A symmetrical design, you got this, you don't need me to say it. A pyramid, P-Y-R-A-M-I-D.
Wait, no, I was lost on the after pyramid.
Oh, no problem. After the pyramid, we had a symmetrical design, a 3D symmetrical design, right? Kids tell me they see a growing pattern because that's all you ever do, Mr. L, is just stupid growing patterns. Wonderful. By the way, you have, Amanda, the skeleton tower. Nobody knows why it's called the skeleton tower, but this is the famed skeleton tower. Raise your hand if you saw something else that Amanda should be writing down. Mr. Ruiz. Quadrants. Oh my God, look at that. There are quadrants. I love it when a kid thinks of something that never in a million years would I think of. What makes you think quadrants, Mr. Ruiz? There's 4 sections. Yes, 4 sections. So I got quadrant 1, 2, 3. Whoops. Oh. It's so great. I'll learn. Let's see how many times I do that today, right? I got quadrants. What else?
Intersection of
I got a cross. Exactly. There's a cross. In fact, there are 2 planes of cubes that happen to intersect perpendicularly at right angles. This is unbelievable. And so now you know that I've got the whole class going. I go, really convince me they're blocks. Well, the little cubey things, dude, right? Convince me I'm going to save 66, so I don't want you counting them, right? What makes it a pyramid? Right? We stop and say, what pyramid? Pyramid is a word you all have to know. It's on the Ames test, right? Pyramids are things that have points up on top and then go down to bases that are squares or things like that. This is a weird kind of pyramid. Wonderful. Thank you, Amanda. What questions might we have? Why? Why am I doing the pyramid, the skeleton tower? The answer is because it is an amazing pattern. Wonderful. Why am I doing this? Yell it out.
Does it really exist in the real world?
Because it what?
Does it really exist?
Yeah, it doesn't. I mean, a good reason is it doesn't really relate a whole lot to the real world. It's just a stupid bunch of blocks. I mean, it's like a children's toy here, right? How tall is the pyramid?
6.
Oh, it is 6 layers tall. How do you know? Because I can see one. Notice I don't touch it. 1, 2, 3, 4, 5, and this guy up here. Wonderful. So I can talk about the number of layers, and I can talk about the total number of blocks. So far, so good? I mean, there are two variable situations.
Yeah, also this is a great exercise for exploring the growth pattern between each layer.
Exactly. So clearly, we have this layer 1, the little dude on top, there's 1 block. Layer 2, altogether, layer 2 has 5, but the whole pyramid,
6,
right, has 6. Oh, interesting. So wait a second. This is now the number of blocks in the layer, and this is the total number of blocks. So there are 5 here, 6 in total. This is unbelievable. The third layer has in it 9. This one's got 1. This one's got 1, 2, 3, 4, and 1. This next layer's got 2, 4, 6, 8, and 1 in the middle. Oh, cool. It's got 9. And so altogether there are 15 in this case. This is really amazing. The fourth layer. Oh, amazing. 14. How did I go from here to here? How did I go from here to here? And from here to here? Ooh. How the hell can it be 14? If it's 4 times something plus 1, doesn't it have to be an odd number, and isn't it really 13? I don't know what I'm talking about. 1, 2, 3, 4. The fourth layer has 3, 3, 3, and 3 wings. 12 plus 1, 13. And then all together, I've got 28. Oh, how interesting. Ready? Your turn. I want you to tell me, for a pyramid with 10 layers, how many and how many? Go.
What's the pattern again? The total is 4 total layers?
No, there's no one here. That was my bad. I'm sorry.
Because this number of blocks on that layer.
9 times 4. Add to 1.
37.
Great. Hey, gang.
It's arithmetic sequence.
So look at what I'm doing here, okay? Look what I'm doing. I've got this sequence and stuff like that. I hear people saying 37. They're saying 37 because the 10th layer, right? The 10th layer has 9 times 4 plus 1, which grows out of these other things. The 10th layer has, right, 4 times 10 minus 3. 4 times 2 minus 3. In other words, if I now did n, this is 4n minus 3. It is a linear pattern. I'm now rushing. I want you to see that this stupid little picture here gives me how many cubes are in each row, how many are in each row. Add 4, add 4, add 4, add 4, add 4. Therefore, I'm able to add 4. I'm able to say, this came up today, right? I'm able to say, hey, look at this. A sub 0 is 1. The first term, 1 cube on top. A sub n plus 1 is always equal to the term before plus 4. This is called an iterative rule. This is called a recursive rule. This is called the add 4, add 4, add 4 rule. This is great, except when I want to know how many blocks are in the 50th row. It doesn't help me. To do the 50th row, I've got to convert this to that the total number is equal to 4 times the row number minus 3. I'm reminding you that we cannot teach quadratics if we don't have a solid base with linear. So that's really this point. But what I've got is this amazing opportunity to start, just to give you some sense of what's possible, right? Where at some point in teaching this stuff, and perhaps not at the beginning, or perhaps as part of the transition, to then say, all right, kids, so this one is linear. And you know what's going on here. First difference, 5. Second difference, 9. Next difference, 13. You with me?
Yep.
Second difference, 4, 4, 4. If the first difference is congruent, the first difference is 4, what kind of a function is it? If the second difference is always 4, what kind of a function is it? So we have a quadratic function. Has anyone figured it out? What is it? You know what it is? Oh, you know the answer down here. Is 100 and what?
90.
Now, did you actually add it up one after the other after the other?
No.
No, you said that when you have an n-layer thing, go ahead.
Well, I just found that between the number of rows and how many blocks there's a multiplication. So
Yes.
like between 3 and 15, multiplying by 5. Between 4 and 24, multiplying by 7. So 5 you multiply by 9.
Oh, look at that. Look at what's going on here. Look at the way in which this analysis says that this 6 is 3 times 2. That the 3 times 5, 4 times 7. Well, wait a second. What are the... That's this number times 3 is this. This number times 5. This number times 7. What the hell? Well, look at that. That's 1 less than twice the number. That's 1 less than twice the number. That's 1 less than twice the number. In other words, mathematics is starting at this level and then building and seeing these patterns and pausing and saying, I'll be damned. So that's n times 2n minus 1. Try it out. N times 2n minus 1, 108, 190. Ready? If n is 10. 10 times 19, I'll be damned. I have a quadratic function, I have a linear function, all embedded in this situation where, as you see in your handout, come on. Some questions you might ask, there it is, describe what you see. We did it, right? How many cubes are needed to build this tower? Well, it's pretty clear, you heard right off, 66. That's not great smarts. What becomes mathematical is now, right, how many cubes you need to build a tower like this? 12 cubes high. I put 10, 12. How many cubes in all? Notice that this thing didn't talk about each layer because this was just a quadratic relationship. I think it's important to see the both put together. And then the big enchilada, how could you calculate the number of cubes needed for a tower that's n high? Bottom line, what's the purpose of math? Bottom line, what kind of items are going to begin to appear on the PARCC assessments, the Common Core State Standards assessments that we're going to face beginning in the spring of 2015? Trust me, they're going to look much more like this than anything that's currently on AIMS. So once again, I go well beyond where we are today and grab you with the possibilities of the picture and using these processes. So, oh no. Oh no, wait a second. I'm a moron. Oh, I know what happened. Very simple. I went and just turned it on without realizing that I created 2 additional slides because Emily said, wait a second. So I'm going to switch over to the other, let's see if I can get out of this. I want you to see 2 important things. I spent all day yesterday doing these 2 stupid slides because Emily told me to do it, and we need to get to them. So allow me to get out of this, come over here, right, and go to, where's my computer? Where? This guy?
Down, right there.
Oh, this guy. That's my computer. There we go. All right, here's my removable disk. And there is, where are we today? We are in Phoenix. Look at this life of mine.
Sign this, sir? Did they sign it down there? I don't think so. I didn't see their names on it.
Hey, gang. There we go. Look at this. That's not bad. So we got this going down, and I knew that what's next is, let's pause. Let's pause for an AIMS debrief, okay? I mean, let's talk turkey about what's on this test and what's important, okay? Ladies and gentlemen, quadratics that we're doing today are important. They're important because they exist in the real world. Done. Convince me, say the kids. They're important because they reinforce all this far more important work with linear functions. Agreed? They're important because they broaden our understanding of functions in general. This notion of as one variable changes, another variable changes. They're particularly important because they are the essence of max-min situations. Parabolas, by their very definition, quadratics have minimums. Where is it cheapest, right? Where is it maximized? So that's why they're important, but come on. Quadratics play only a very small role in raising AIM scores, and I just think that we're irresponsible if we think that somehow the answer is doing a better job of teaching quadratics. Come on, gang. Your AIM stuff. Meet. You realize that all this hoopla is about kids meeting the standard, which means that 52 raw score, or 61% of the points, is all a kid needs? This is not a secret to you, right? You all know?
It's enough.
You all understand what I'm saying? That in fact, when somebody says, oh my God, look at this, the kids suck on the benchmark test on polynomials, your appropriate response is, who cares? I'm not going to waste 1 microsecond trying to teach kids polynomials to raise test scores when I need to spend a whole lot more time on the data and the linear functions and the representations than on polynomials. Because if I do a better job on that stuff, and who cares if they never see the polynomials, they will all pass the test. Because I'm sorry, this is ridiculous. You failed kids at 61. So we need to understand what's on that test, right? The high school sample test. So I'm looking online, the high school sample test. 4 of 42 items are quadratics, and that's really pushing it. Yeah, but that's the sample test. We know that that doesn't really represent the real test. So we go to the 2010 released items. There are 30 released items. I've seen them all over Phoenix. You guys clearly know about them. 5 out of 30 are quadratic. Oh my God, I have to teach kids how to factor. Oh my God, I have to teach kids how to do all this stuff. So let's look at those 5 items. Ladies and gentlemen, in 2010, kids did reasonably well on a table. 1, 1, 2, 4, 3, 9, 4, 16. I'm sorry, but if you're going to tell me that that's quadratics, that's 7th grade mathematics. This says, what's the relationship between the first number and the second number? If you don't know, or if you haven't got kids to see that 1, 4, 9, 16 is square numbers, I'm sorry, you can't tell me I got to do factoring to do that. But we ought to be embarrassed that only 72% of our kids can tell us that the rule in a multiple choice thing, where all the other ones are linear. Am I making sense to you? That it's about understanding this stuff and seeing what's actually on. Oh my God, evaluate. A squared plus absolute AB for A equal minus 4 and B equal 3. Now, I grant you that that is hard. I grant you that any number of kids square this thing and think that it's minus 16. We know how many kids don't know what the hell those lines mean and what absolute value is, but you can't tell me that this is quadratics and factoring and simplifying rational expressions. This is bedrock stuff that is evaluating things where we deal with some absolute value and all that kind of stuff. 61% of the kids, I'm not sure how much I worry about that. Certainly I worry about this a whole lot less than this one. And then what was on this release test? There you go. Which graph represents x squared plus 2? I'm sorry, but if we don't have kids comfortable enough, as we were talking before, about the issue of graphing lines and how important it is, and then we move to x squared. Excuse me. We said in an earlier visit that every line is a transformation of the 45-degree angle y equal x line. And that every line in the world is either and or an up-down transformation and or an angular transformation. That you take this y equal x line and you move it up or down so that it has the right y-intercept, and then you tilt it in some way, you rotate it, and then you get every other line. Well, it's just as clear that every single quadratic looks like this or this. It looks like this unless it's translated down this way. Or it's translated out this way, or this way. Right? And so this notion of x squared, y equal x squared, I think that again, that's 8th grade. That's this notion when I'm first doing exponents. If all I do is say, when you square a number, you multiply by itself. And I miss the opportunity to grasp them. If I miss the opportunity to see what they look like, then, so that to me is bedrock and what to be part of the curriculum. And 2/3 of the kids is all that can do that? That ought to worry us. But clearly, that's not asking kids to go and And then we have, the graph shows the height of a football. This is really stretching that I call this quadratics. But since it is a parabola, and the question is, what's the maximum height? Which means, right, what is it? I didn't say how many seconds does it reach the maximum height. No. This was as simple as, there's the maximum, 37. This is reading. This is, again, a 5th grade skill. Understood? But it's quadratic. I know, it's quadratic. And I'll grant you that, yes, we spend how much time on the one stupid item that appears on the Ames 2010 test. What are the solutions to? And less than half the kids get it right, and you know that probably 80% of those kids got it right because they picked and plucked in the multiple choice answers. Which is exactly what I want kids to do. So the lesson here is, look what I've done. The lesson here is, number one, quadratics are more important than ever. This one. Quadratics is more important than ever. But quadratics for the sake of the Ames test is absurd. Right? It's quadratics so that kids actually see what goes on, and when you see what is the bedrock, I chuck this one. I don't worry a whole lot about this one, although it's not a whole lot of things, and we ought to be embarrassed that kids can't do the others. And so my question to you is, what becomes important? And so what becomes important, I think, there you go. Tell the person sitting next to you what the 4th stage looks like. Great, so watch this. Watch this. So, stage 4. Wonderful. On your mark. Get set. Sir, you said that.
I saw the middle, and ever how large the middle gets, the sides get the same. So, like the first one, the middle is only 1, but the top and the bottom is only 1.
Wait a second. Wait a second. The middle is 1, and then you've got 4 arms that are each 1 in stage 1. Wait a second. In 2, you have the middle equal n, plus you have 4 arms that are each n. Fascinating. In other words, the rule is 5n. Let's see if that works. 3rd stage should have how many blocks? 3rd stage should have how many blocks? 15. Does it?
Well, there's 2 missing.
Stage 3?
17.
Oh, so in other words, sir, you want to amend your rule? Thank you, plus 2, exactly. You see, we checked it, we said, oh, that doesn't make any sense. Well, yeah, because it's the middle 2 plus the 4 arms, but then you have the 2 at each end of the middle row that are stuck there. Oh, interesting. And they're there in every one, so that changes the rule a little bit. Who saw it differently? Describe the 4th stage. Oh, come on. Yeah, ma'am, listen to this.
I saw it 9, 9, and 4.
Oh, in other words, you saw 3, 9, 9, wait a second, for the 4th stage?
So it would have,
yes.
like, so I'm seeing the middle chunk is the stage number.
Yep.
And the legs or the vertical parts are.
So look at this. I see 2 vertical towers that appear to each be 2n plus 1.
Yeah.
Plus, I see a middle thing that looks like n. So I've got 2 times 2n plus 1 plus the n. Which, as you all well know, is the same as 5n plus 2, but I'm not going to tell that to kids. I'm going to have them describe this. Who can describe it differently? How did you do it, ma'am?
And so you're just adding 5 each time.
Oh, cool. So in other words, I have no idea what's going on, but I add 5 every time, and so whatever 3 was, I'm going to add 5 and I'm going to get 4. I'm going to add 5 and I'm going to get 6. How nice. I naturally have kids give me an iterative rule. I love that because this 5 and this 5 are the rate of change. You know that that's what's going on. You know that over 3 weeks of instruction, that's what I need kids to take away. Right? That idea of the 5. Wonderful. Why is this discussion so important? Because how you see it, how you describe it, now allows you to describe the 10th stage. And I have a simple question. How many blocks do you need for the 10th stage? Ooh. Ooh. And some of you go right to the rule, some of you go back here. Well, of course, I mean, just look at this. The mere fact that somebody went to the rule and is screaming it out, and other kids are going, +5, +5, +5, is all that we need in the class to understand there are lots of ways to get right answers, but what mathematics is about is being efficient. What a function does is it describes a rule between 2 variables. And gang, look at this. I know, it's just they're driving me crazy here. I put my thing in and
Touch the board.
I know I can touch the board, but
There's something up in the corner. No, the left corner. Bottom left corner.
oh, there it is. It's, you know what? When I come to Phoenix, nothing works. So I have this personalized pattern. It's a pattern shown below is continued. How many squares? Look at the method to my madness. I start with a picture. I build this thing. We say describe it. I then move to the 10th figure, the 100th figure, the nth figure. And by the time I get to the 100th, it's clear that I need a rule of some sort. I'm rapidly moving beyond the iterative add 5 rule and beginning to do it. But look at what happens here when I now say to kids, go and build. See, this is why I demand, why I've been requesting that Emily supply the handouts. I mean, you need to know that you walk out with all this. You know that you can translate this into your own PowerPoints and your own smartboard kinds of things. But the important issue here, if I'm going to build a foundation for quadratic functions, is that I build a foundation with linear functions. And look at this thing that my wife and her co-author are really the creators of. I've never seen, outside of Ann's stuff, this 3-column T-chart. We all have the figure number and the total number. Look at how, helping in Algebra 1A and in Algebra 1B, this idea of what's going on. Now, the color didn't work. These are obviously the pinks, right? Those are the pinks, the extra ones there. Every one of them has those too, and then 5 sets of 1 purple. I can go back and redo this your way with, I have a row of 3, a row of 3 and 1 more. A row of 5, a row of 5, and 2 more. A row of, and build this thing in that same way so that I see what goes on, but look at how this what I see sets up the 2 plus 5n. A representation of function rule. I have everything but a graph sitting here in terms of, now, what's a function? How do you know it's a function? How does it play out? Right? The constant shows up clearly 2, 2, 2, 2, and the rate of growth shows up as 5, 5, 5, 5. I think that's pretty powerful. I think that if you just pause and think about what we've been talking about in 3 different meetings today, so I need to give kids a reason to solve equations. Good news. Parking at the amusement park is $3. Costs you $3 to go, sorry, it's $3. It costs you $2 to go on every ride. Every one of you should now be conceptualizing 2 times R, 2 times the number of rides, plus 3 is the total cost. And you know that all of mathematics is, I want to go on 10 rides. How much will it cost? Or the stuff that you're all up to your neck in, I only have $52. How many rides can I go on? Now there's a reason to solve it. By the way, that notion of solving equations as undoing becomes clearer after we've done the literal, after we've done the evaluating the thing. You see that I plug in 9 rides. I multiply it by 2 for each of them, and then I add 3. Well, duh, if I got $50, then lo and behold, 52. I take the 3 away and I divide the 49. The rate of growth shows up and I build that sense. Again, a 2-day lesson or a full 90-minute lesson that I'm reducing to 12 minutes on the assumption that you understand how I think it's irresponsible to come in here and just start with quadratics without helping you see the quadratics building off of this stuff. How I want to also have these tables and go from there. And so, good morning, boys and girls. You are lucky as all get out. because we are going to now climb the Algebra 1 mountain, and we are going to do linear expressions and equations and functions with decimals and weird things, and I put the 9 on the left and all that stuff, and you're sitting there going, who cares? Class has been hired by a company that makes all kinds of cups. Foam, hot cups, plastic cups, little cups, big cups, and all that kind of stuff. So I got this wonderful cup sitting here, right? And I put another cup in. What happens to the height of the column when I put another cup in? It grows. Why does it grow? Because it stacks. And I put another cup in, and I put another cup in. Wonderful, right? You will examine several different kinds of cups and make recommendations about packaging cups. You tell me, you mean to tell me that you can't go to Piggly Wiggly and Albertsons and Publix and Safeway and go to McDonald's and go to, I teach math. We're doing all this stuff, but McDonald's is only too happy giving you those ridiculously big cups, like big gulp things, and you only need 10 of these cups. And then every group of kids in pairs has a group of cups. And what's the question? How many cups? How tall a stack? Is this a linear or quadratic relationship? Linear. Why is it linear? You understand. All you need to know about linear functions, if you say, well, obviously it's linear, you jerk, because you're adding. You're adding the same amount each time. Oh, cool. So, in fact, I have. In fact, what I end up with is this. Tell me about these cups. Well, obviously these cups that are stacked are 1 cup. 9. 9 inches tall. Plus 1/10 of an inch. 9/100ths of an inch for each additional cup. Where's that x minus 1? Oh, I don't count the first one, each additional cup. Oh, neat. And you know what, for most of you, this makes no sense. It is insane for me to go from this to that. So instead, in a group of 3, measure the heights, measure the height, do the table, round it to the nearest centimeter, graph your data. I now have 20 kids working in pairs, and I have a document camera that allows me to now go, tell me about your data, tell me about your graph. How is this related to this? Is it clear to you that if I'm going to get kids comfortable with y = x squared plus 2, if I'm going to have kids comfortable with, what happens with x plus 2 times x plus 7, which is where we're going, then I need to know, first of all, that they're comfortable with, 9 plus 9/10, whoops, 9/10, good, 9/10, and then look at this graph. It's obvious, it's sitting there, okay? So I have this. Make sense? Where is the 9 in the graph? Ooh. Tell the person sitting next to you where this 9 is in that graph. 1, 9, 10, 9. Why is that 1, 9 there? The number of cups, the height. Wonderful. You ready for this? Suppose that you had no cups. What does it mean that when you have no cups, you have a height of 8.1 centimeters, or whatever, centimeters? What does that mean? It's creepy. It doesn't mean anything. I mean, in this case, it's like you can't have no cups, dude. I mean, what I've just done is I've given kids for the first time a reason to talk about the range and domain. In fact, this has no meaning if the domain is anything other than whole numbers. Well, you take a half a cup, it doesn't have a lip, right? It's got to be the whole cup. And so the range, the domain is very distinct. The domain is 1, 2, 3. It is the series of counting numbers. And my range is a series of numbers that fit. So I actually have a step function. Watch this. Now explain it. Do you see the difference between a focus on the answer? Boys and girls, your job is to solve this equation. Your job is to graph this equation. Is the very last thing we would do. Because first we've given that equation life. Because first we've said what gives us relationships like that. What do they look like in a table? What do they look like in a graph? And can you explain it? And you think the kids are going to have trouble on the Ames test? When they've been in a class where 8-ounce hot cup, that's what I have. The explicit rule is 9 plus 0.9, that's the same thing. In this rule, 9 centimeters is the height of one cup, including its rim. You must multiply 0.9 by the number of cups minus 1, because each time you add a cup, the height increases by 9/10 of a centimeter, and you must subtract 1 from the number of cups because the first cup already includes the rim, and that's already been accounted for in the change. Oh, cool. Look at this. In the real world, gang, you don't get nice data. In the real world, the kids have got measurement error. I love this. I love the fact that this kid has a different cup, therefore a different rule. And this kid doesn't have 2.3, 2.4, 2.2, and then sits there and says, whoa, goodbye, Broderick, get out of here. Get out. Goodbye. Yes, look at that, takes the median. Now, I don't know whether you want the median or the average or all that kind of stuff, but I frankly think that that's brilliant. I want to have kids talk about, right, how much does it go up over 8 jumps, right? Actually, 7 jumps, right? So we're doing slope. I'm not sure. Do you understand that we're actually doing slope? That's what that 2.3 is. That's the rate of change. Am I making sense? That's what that rim is. Now, I don't fool myself, right, into knowing that some of you are sitting on the edges of your chair following everything I'm doing. There are some of you that say, wait a second, I want to go home tonight and try this out. And there's some of you saying, oh my God, he's going 10,000 miles an hour, I don't know what the hell he's talking about. I understand that. But that's what a PLC does. The PLC says that some of us go back and try this back at the ranch. And we videotape it. And we share it with others. And we recognize that the first time we do it, we fall flat on our face. That even if we do it in front of a mirror, even if we do it with our brightest kids, that this is not easy. This is so different than how we've done it. But look at it, it's not an experiment for the sake of an experiment. It is an experiment to gather data that I represent in a table, and then I go and I graph in some way and all that stuff. And so gang, look at this. How is your graph similar to those of other groups? How is it different? Explain the real world reason for the comparison. What the heck kid is going to sit there and go, why are we doing this crap? No kid's going to say that when they're playing with these cups. And well, our graph is similar in the way that all the graphs basically show a line of points. This happens because each stack increases, but in fact, they are different. I think this gives it. But our graph is different because our starting point, the height of one cup, was different. And because the amount of the stack changed because the cups were different sizes. Our graph is different from some others because our lines cross each other. This happens because, oh my God, they cross each other? No, 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 no. Your turn. I would like for you to describe the blue cups vis-a-vis the red cups. Go. Tell the person sitting next to you. Ladies and gentlemen, this tells you that. This tells you that the red cups are a little bit taller than the blue cups, although they seem like they're just a little bit taller, right, than the blue cups. A little bit taller, right? And then what happens? Yell it out.
The red cups stack better than the blue cups.
The red cups stack better? What does that mean, they stack better? There's smaller amounts with each integral. There is a smaller rim attached to it. It may be that, in fact, the big cups stack beautifully, but there's a big, fat, ugly rim on there. You know, those McDonald's cups with the styrofoam that's got the rim around it that sticks out that you burn your tongue on, right? You know what I mean? So, interesting. If you can't interpret that, then how have we really been successful? So look at where this goes. On your mark. The kid says, this graph tells us that cup 1 has the larger rim than cup 2 because every time another cup 1 is added to the stack, the amount of change is more than, and therefore they intersect. And so when we talk about systems of equations, my God, I have systems of equations. The question is, if I got this little cup with a big rim, and I got this big cup with this teeny rim, the question is, when are they the same? What number of cups gives us the same size? And it's like, well, duh, right? If you saw the two cups, they'd be very close in size. Aha! But one would have a larger rim, so when you stack them, the stack of the shorter cups would go up by more each new cup. Now, if that isn't a kid that's communicating understanding, I don't know what is. Your turn. Tell the person sitting next to you what's true of the orange and the puke green cups. Oh, they're parallel. Yes, the cups are parallel. No, you goon, the lines are parallel. Answer, what's the same in both cups? The rim is the same, how do you know? You see that questioning? It was really neat today at South Point and at Tempe Accelerated. Because there were times when I'm sitting writing all these notes and I watched people in this room ask a question and immediately without batting an eye go, really? Why? And I just sat there and went, yes. And sometimes it was like, the hell are you asking? You know, it was almost like, well, Steve's in the room, so I better ask why. There were other times when the kids just jumped in because you asked why already, and they know after 5 weeks. And there were a whole bunch of other times that, as you well know, the kids said, 84. Oh, good, next problem. And if that's what we do, then we're racing through. And so when we start the day off with, we listen to you, we're nuts. We spend time to really make graphing lines and what they mean real. It means that we asked more questions, it took more time, but the hope is it made sense. What's true of the height of the two cups? Clearly the green cups is 2 centimeters smaller. You can almost picture them. Look at the picture helping us picture the cups in some way. And so the two cups look alike, except that they're about 2 centimeters taller. How nice the way. The rate of change in the graphs is the same because the rims of the cups must be the same size. These kids understand it. And so what is it? Why am I doing this? This ties right back in to quadratics are important because, and so I go back and say, let's build the foundation. There's payoffs in the symbolic world when we start with these things. First of all, kids experience modeling linear functions. My job today is to take this to modeling quadratic and linear functions. Real-world references for slope and intercept, it makes sense what those things mean. And not quite a y-intercept, but in that cups thing, it's the x equal 1 intercept. And it's a great benchmark for functions whose graphs are parallel and why they're parallel. And in fact, what should be on this list is, and when you have two cups, it's systems of equations. And sometimes they never meet, and sometimes they intersect, and all those kinds of things. So your turn. We just spent 3 days doing all this cup stuff and these graphs, and you're writing it, and we're doing the homework. I say to you, I say to the kids, what's a function? Do you now understand what a function is? How can I represent functions? And you sit there and go, well, duh. You can put it in words. You sure can. You can put it in a symbolic form. It looks like an equation. Cool. You can put it in a table. Yeah, you can graph it. Why are functions useful? Are all functions straight lines? Aren't those the critical questions that are there? And they're worth 5 minutes apiece. I mean, that's partially either our formative assessment or we start with it. I think that now what we have is this sense of the foundation. And you know that this foundation will carry over to most of the AIMS test items, both the linear ones and to the quadratic ones. Good morning, boys and girls. So, I'm tired of these linear functions. They're just too easy. Lines are a dime a dozen. So, what's an n-gon? I can't hear you. What's an n-gon?